Now I'd like to talk to you a little bit about pistons and the way pistons behave. There's two types of pistons, single-acting ones, single-acting cylinders, and with these, the power stroke is the stroke where you blow the air in. So here we blow the... Oh, that's the wrong thing to have, hold on. We blow the air in there, and the power stroke is outwards. The spring is assumed to have no power, just enough power to push the piston back. And this one, we blow the air in there, and the power stroke is outwards. So that's single acting. It only has power stroke in one direction. Or we have double acting, and double acting has power outwards and has power backwards. It's a double acting cylinder. In addition, there's some other symbols here. We've got this symbol here. That's a magnet. Any idea why we put a magnet in the middle of the piston? We put a magnet in the middle of the piston so that we can detect where it is. We put a reed switch there and a reed switch there, and you can tell where it is, whether the thing is in or out. Now, one big problem we have with pistons is that if they're any sort of length and they have any sort of pressure on them, when they get up a lick of speed, they tend to get to the end of their line and smash right through the end of the cylinder, which is a big problem. To fix this, we use a thing called cushioning. What we have is like small sub-pistons inside the main piston, sub-piston. And as this thing comes crashing towards this direction, the sub-piston engages in a very, very tight hole in the casting. And from that hole in the casting, there's a very thin air line comes through. And as the sub-piston engages in that hole, it cushions the thing. So it basically breaks it to a halt in a nice cushioned way. Now, the air hole is variable. So by having this cushioning, we prevent the piston blasting out the end of the cylinder. So these symbols here, they're cushions. That's a symbol for a cushion. And this symbol here, that's variable. Just like in electronics and electricity, an arrow through something means variable. So these have got variable cushions, and what that means is when the piston comes to either end, it doesn't smash right through. It goes crashing along and then slows down at the very end as it's cushioned to a halt. Here are some symbols. Now, anybody wanting to go into this in more detail, I've found a very good site, and I'll just see if I can pull that up. I found a very good site. It's done by the BBC. And hopefully there it is. If you can see this, I just published the URL there. And it goes into this in some more detail. There's pneumatic symbols there. Can you all see this on your computers at the moment? Okay, so there's the first page, and it goes into it in some detail. And then it goes through, and... okay, the next page. it shows you how this sort of thing works. It's a little bit simplistic. It's meant for school children. But, you know, if you want more details of how it's explained. And here we've got some typical symbols. I've got a 3-2 valve there. There's a unidirectional flow controller there. And a single acting piston. And when I press the play button, the piston comes out. It goes gradually more complicated. So here we've got a shuttle valve shuttling over and a double acting piston coming out. I can press the other side and it goes back in. It's all very pretty. And here's the diagram for that. What I'd expect you to be able to do is look at this diagram and work out where the air is going and how it all works. So hopefully you can interpret this type of diagram. Even more detail. Here's a time delay circuit. So you can use this. It's quite useful and help you get through the exercises in the book. Get rid of that. So looking at this simple system here, just to make sure you can interpret this, what we have here is a 3-2 valve. It's got 3 ports, 1, 2, 3 ports. And it can be in 2 positions. When you push this down, here we've got a block. That's the block for its de-energized state. When we push the button down, it goes to this state. When we push the button down, air from the air supply is connected across there, and the piston comes out. Hopefully fairly easy. It's quite common for us to use Lockoff to lock a piston in place. Here's a piston with Lockoff. What we've got here is a 3-position switch. It's a 5-port 3-position switch. It's called a 5-3. In its central position, the cylinder is locked. If air can't come in and air can't go out, then it's locked. It won't move. We use this as a way of locking cylinders in place. Now, here I've pushed it to one position and the piston goes one way, because I've put mains air on the top and it goes in. Here it's locked. Now it's locked inwards. Air can't get in, air can't get out. The cylinder's not going anywhere. It's locked. Now, a funny thing happens if we get a leak. I'm going to introduce a leak, and the leak is here on the piston seal. My piston seal is leaking. Now, this is what happens. I've got mains pressure, just going back, I've got pressure here. This side of the cylinder is pressurized. If I have a leak on the piston seal, this is what's going to happen. It's going to slowly come outwards. Now there's no air in, there's no air out, but my piston is coming outwards. And there is no air in or no air out, but the cylinder piston keeps coming outwards until it's fully extended. Now, if there's no air in and there's no air out, why did that piston just come out? Any ideas? Just to help you with that, what's happened is the air has passed from, let me just get it on. The air has passed from this side of the cylinder into that side of the cylinder. And what's happened is the air pressure has equalized on both sides of the piston. If the air pressure equalizes on both sides of the piston, the piston comes out. Any ideas why? I'll take any kind of wild guesses.
Can't hear you.
I forgot to turn the thing back on. It's all to do with surface areas. The surface area, hang on, I'll start that again then. The surface area on the back side of the piston is that. The surface area on the front side of the piston is that. The difference between the two is that on the front side of the piston there's a shaft coming out. So the back side of the piston has got a bigger surface area as the front side of the piston. And because force equals pressure times area, there's more force on the back side than there is on the front side. What that means is, if you ever get the situation where the pressure is equal on both sides, the piston will tend to come out. It's a magical thing to see happening. People don't believe it, but it's a classic example of a leak. If you have a leak on the piston seals here and here, if you have a leak on those seals, the piston comes out. That's something to bear in mind, because basically the failed position of a piston is out. Pistons will fail outwards. So when you're designing systems and you're designing engineering systems, you need to design them so that their safe position is with the piston extended. Because in the event of the seals breaking and the seals passing, that piston will extend. I've seen it on hydraulics, and people have said, we don't understand why the thing's still moving. We've turned off the hydraulic pump and it's still moving. It will move. There's absolutely nothing you can do to prevent it moving apart from repressurizing the other side of the piston. So this is something to bear in mind. Safety implications: a piston will fail outwards. And if you ever see this fault, if you ever see a fault where a piston is slowly creeping outwards when it should be in its lock position, then the fault is that the seals are leaking. And the reason why it creeps out is because of the magic of surface areas. The back side has got a bigger surface area than the front side.